Welcome to this hands-on machine learning tutorial where we dive into the world of natural language processing using RNNs. In this project, we're building a character-level text generation model from scratch using Python and PyTorch. Our goal? To teach a simple recurrent neural network to understand the patterns of written language and generate new text, one character at a time. We'll start by working with a small but rich corpus of text drawn from classic fairy tales and then prepare the data so the model can learn from character sequences. You'll see how we split the data into input and target sequences, encode characters numerically, and train the model to predict the next character in the sequence. By the end of this project, you'll have a working character level RNN that can generate coherent and creative text that mimics the style of training corpus. So, if you're ready to step into the magical world of text generation and recurrent neural networks, let's get started. Before we dive into building our recurrent neural network, we start by importing the essential libraries: PyTorch for building and training the model, NumPy for numerical operations, and Python's built-in random model for reproducibility. Next, we define our sample text corpus, which will serve as the training data for our RNN. This time, we're using a slightly more complex and expressive corpus, a beautifully written passage from a classic fairy tale. The corpus is rich in vocabulary, sentence structure, and punctuations, making it a perfect challenge for our character level RNN to learn them. Our goal will be to teach the model to understand the flow of characters, capture sequential dependencies, and eventually generate coherent text that resembles with our original story. With our data in place, we're now ready to move forward and prepare it for model training. First, we extract all the unique characters from the corpus and sort them to build our character vocabulary. This gives us a complete mapping of every character the model will encounter, including letters, punctuation, and white spaces. We then create two essential dictionaries: character to index to convert characters to their corresponding numerical indices, and index to character to reverse that process and map indices back to characters. These mappings are crucial for encoding our data into numbers that the model can process and for decoding the model's prediction back into human readable text. Finally, we define a fixed sequence length, in this case 20 characters. This means our model will look at 20 characters at a time to learn patterns and predict the next character in the sequence. With pre-processing complete, we're ready to generate training data from our corpus. In this block, we define a function called createDataset that prepares our text data for training the RNN. The function takes in the full text corpus and a specified sequence length. It then generates two lists: X data for the input sequence and Y data for the target sequence the model should predict. We iterate over the text, extracting character sequences of sequence length as inputs and their corresponding next sequences as targets. Each character is now converted into a numerical index using the earlier created character to index dictionary. This transformation allows the model to work with numeric data rather than raw text. Once the sequences are processed, we convert these lists into PyTorch tensors for use in training. Finally, we call this function using our corpus to create the datasets X and Y, which will serve as the input and target data for our character level RNN model. In this block, we define our RNN-based character level language model by using PyTorch. The class character RNN inherits from nn.module, allowing us to build a custom neural network architecture. Inside the constructor, we first define an embedding layer, which converts each character index into a dense vector representation of hidden size. This helps the model capture semantic relationship between characters more effectively than one-hot encoding. Next, we define a simple RNN layer that processes the embedded sequences. The RNN takes in the embedded inputs and returns the output sequences along with updated hidden data or hidden state. Then, a fully connected layer maps the RNN output to the size of the vocabulary, effectively predicting the next character at each time step. In the forward method, we pass the input through the embedding layer, feed it to the RNN, and finally apply the fully connected layer to the output. This method returns both the final output and the updated hidden state. Following the model definition, we set some hyperparameters, specifically the hidden size, number of layers, and learning rate. We instantiate the model with these parameters and define the loss function and cross-entropy loss, which is suitable for multi-class classification like character prediction. We also set up the Adam optimizer to update the model's parameter during training. Alright, everyone, now that our model is set up, it's time to train it. We start by setting the number of training epochs to 200. That's how many times the model will see the entire dataset. Inside the training loop, for each epoch, we first initialize the hidden state of the RNN with zeros. This is important because we're not maintaining state between batches in this setup, and we want each sequence to be treated independently. Then we pass the input data X along with the hidden state into the model, and it returns the predicted outputs and the new hidden state. The output of the model is a 3D tensor, but to calculate the loss, we need to flatten it. So we reshape both the predictions and the actual labels using .view -1, vocab size and .view -1 respectively. This aligns the dimensions so that our cross entropy loss function can compute the difference between predicted characters and actual ones at each position in the sequence. Next, we zero out the gradient using optimizer.zeroGrad, performing backpropagation with loss.backward, and then updating the model's parameter using optimizer.step. To keep track of the training progress, we print out the loss after every 20 epochs. This gives us an idea of how well the model is learning over time. Basically, a decreasing loss indicates that it's getting better at predicting the next character. So by the end of these 2000 epochs, we should have a model that's pretty good at generating text based on the corpus and the patterns it has learned from our corpus. Great. Now that our model is trained, we'll see it in action by generating some text. In this final block of code, we define the generate text function. Here's how it works. We start with a seed string, start sequence, and a desired length of the text we want to generate. We convert the characters in the start sequence into their corresponding indices using character to index mapping and feed them into the model. The hidden state is initialized to 0, just like during training. The function then enters a loop that runs for the number of characters we want to generate. For each step, we pass the current input and hidden state into the model. The output contains the model's prediction. Specifically, the last time steps output holds the prediction of the next character. We apply a softmax to convert the raw scores into probabilities and then use torch.multinomial to sample the next character index based on those probabilities. This adds a bit of randomness to the generation, making the output more natural and less repetitive. The new character is appended to our output string and we prepare the next input with this newly generated character. Finally, the full string is returned. So let's interpret the output we generated with this. So this is a promising result. The model has learned to mimic the structure, style, and even vocabulary of the input text. You can see that it continues in a grammatically coherent way, maintaining the theme and narrative tone of the original fairy tale. Of course, since our dataset is small and the model is relatively simple, the generation might become repetitive or drift off track if we generate longer sequences. But this is a solid demonstration of how RNNs can learn from a character level data to generate text character by character. With a larger dataset and perhaps more training time or layers, we could produce even more convincing stories. And that brings us to the end of this exciting project on character level text generation using RNNs in PyTorch. So throughout this journey, we started with a simple fairy tale style corpus and explored how to build a recurrent neural network that can learn patterns at the character level. We covered everything from text pre-processing and data creation to defining the RNN architecture, training the model, and finally generating the new text. The output we saw may have been short, but it was meaningful. Proof that our model could pick up on language structure, punctuation, and storytelling flow from a very limited dataset. With a larger corpus and deeper architecture or more advanced techniques like LSTM or GRU, the quality of generated text can improve even further. Projects like this are a great introduction to natural language processing, especially when working with limited data. They help us understand the fundamentals of sequence modeling and set the stage for more complex applications like chatbot development, language translation, and text summarization. So if you enjoyed this project, don't forget to like, share, and subscribe for more hands-on AI, ML, and deep learning tutorials. See you in the next project. Until then, keep exploring and keep learning.